Bismillahirrahmanirrahim. Welcome to the fourth lecture of Mechanics of Solids. In this lecture, we are going to discuss another very important type of stress that is called average shear stress. In one of the previous lectures, we have defined shear stress as that component that acts in the plane of the sectioned area. However, in this lecture, we are going to see what is the average shear stress. Let's consider these two plates that are joined at this location. If a vertical force is applied at this point, it is apparent that it will try to break this bar along this AB and CD plane. Thus, in order for this bar to remain intact, two vertical forces must act at this AB and CD plane to resist this vertical force F. These two forces are called the shear forces, and each of them on one of the faces is equal to one half of the applied force. Now if we move forward and take an average effect of this force, we will find that it is actually equal to the average shear stress. Note that average shear stress is in the same direction as this vertical force V, because all this stress must add up to resist this vertical force, downward applied vertical force F. The loading case discussed here is an example of simple or direct shear. Since the shear is caused by the direct action of the applied load F, this type of shear often occurs in the simple connections such as bolts, welds, and when two materials are joined by glue or some kind of adhesive. Although a more precise investigation of the shear stress distribution over the section often reveals that much larger shear stresses occur in the material than those predicted by this equation. However, this equation is still acceptable for most of the engineering design and analysis. Engineering codes allow its use when considering design sizes for fasteners such as bolts and for obtaining the bonding strength of glued joints subjected to shear loadings. Let's consider a volume element that has been cut from a material that was subjected to this stress tau zy at this location. Now, equilibrium requires that this stress must be accompanied by stresses on all the three faces of this volume element. Let's consider the force equilibrium in y direction. Force equilibrium in y direction requires that this tau zy multiplied by del x and del y, which are the infinitesimal area elements, must be resisted by this tau zy dash. Similarly, it will be multiplied by the same area elements. And since sum of forces must be equal to 0, this means that the shear stress on the top face of this element is equal to the shear stress on the bottom face of this element. We can reach to the similar conclusion by considering a force equilibrium in the z direction. We get to this conclusion that the shear stress on the left side of this element is actually equal to the shear stress on the right side of this element. Now a question arises, is there any connection between the shear stresses, these vertical and the horizontal shear stresses? We can answer this question by taking a moment along this x-axis. If we are taking a moment along the x-axis, we have to ignore this tau yz dash and tau zy dash. Okay, so these two stresses, or the forces due to these two stresses, will cause a moment about x-axis. Thus, we have the tau zy multiplied by the area and multiplied by this delta z, which is basically the moment arm for this shear force. And just by applying the summation, we get to this conclusion that the vertical shear elements are actually equal to the horizontal shear elements. This is called the complementary property of shear stress, in which we say that the shear stresses act on the opposite edges of a volume element, and the four shear stresses on the four faces are actually equal. How can we determine the average shear stress in any element? It basically requires two steps. First is we need to section the element at the location where the determination of average shear stress is required. Then we draw the free body diagram at that particular location. After drawing the free body diagram, we will get to know how much shear force is acting at that location, and then we determine the area at that location, and from the ratio of shear force and the area we can obtain the average shear stress. We will discuss some examples in the coming slides to get this point clearly across. This is our first example. In this we need to determine the shear stresses at the point A and the point B. This is a bar that is supported by two pin supports at point A and the point B, and a vertical load of 30 kN is applied at a distance of 2 meters. As I have mentioned that first of all we need to draw a free body diagram of this element. So if we draw a free body diagram of this element, we'll get to know that we are having this AX, AY at this location, this pin location, and this B is actually supported by this inclined force F that is exerted by this point and by this pin C. Now first of all we need to determine the values of these forces, which can be determined if we take a moment about point A. Since point A is a pin supported joint, so it will not take any moment. Thus taking the summation of moment is equal to 0 at this point, we get this equation: 30 kN multiplied by this 2 meter, and this will be a clockwise moment. This vertical element of this FB force will cause an anti-clockwise moment of this much value, and from the summation of this equation we can obtain the value of FB. Similarly, if we take a summation of forces along x-axis, we can determine the value of AX, which will be actually equal to the horizontal component of the force FB, and the vertical component of the reaction at A will be equal to the vertical component of the force FB, and will be equal to the sum of the vertical component at the force of the force FB and this load 30 kN. Thus it comes out as 20 kN. Now we know the forces at the points where we want to determine the shear stress, and from this we can determine the average shear stress. The resultant force acting on the pin A is obviously just the sum of AX and AY square taken in the under root, and this comes out as 21.36 kN. It is very important to note this thing that the pin A is supported by two fixed leaves, and so the center segment of the pin has two shearing surfaces between the beam and each leaf. The force of the beam, 21.36 kN, acting on the pin is therefore supported by shear force on each of these surfaces. This is called double shear, and this is actually equal to 1/2 of this applied force of 21.36 kN. On the other hand, if we consider the force or the shear at the location of B, we'll come to note that the pin B is only subjected to single shear, which occurs on the section between the cable and the beam. Thus, for this pin segment, the shear force is actually equal to this the horizontal force acting on the point B, that is 12.5 kilonewton. The average shear stress can be calculated by simply dividing this shear force VA by the area of this pin. Has been calculated by simply multiplying the square of diameter by pi by 4, and similarly shear stress has been calculated at the location of pin B as well. Here we are having another example in which we need to determine the compressive stresses on the faces AB and BC and the shear stress acting on the face BD. Before solving any problem, the first step should be the free body diagram. If we draw a free body diagram of this first element, in which we need to determine the compressive forces on face AB and BC, we'll get to know that this AB and BC force are actually the vertical and the horizontal components of the applied 600-pound force on this inclined surface. Similarly, if we draw the free body diagram of this section DB, we'll come to know that section DB is experiencing shear stress because of this horizontal force acting at AB. Obviously, if a force is acting at AB, it must be resisted by an equal and opposite force at this face, so that the shear failure do not occur at this location. Let's go back to the first step, that is the actual determination of the values of these forces FAB and FBC. The FAB horizontal force is equal to the horizontal component of this inclined force, and we have determined it here FAB as 360 pounds, and the force FBC, again since it is a vertical component, it has been determined simply by the summation of the vertical forces, and it comes out as 480 pounds. This 360 pounds is again the shear force applied at this location of DB, and thus the shear force at the location of DB is 360 pounds. For the determination of stresses, the procedure is quite simple. We just need to divide the forces with the respective areas, and we have done here so. The compressive stress at the location AB comes out as 240 psi, and the compressive stress at the location BC comes out as 160 psi. It is important to note this thing, that whenever we need to determine compressive or tensile stress, it is actually the normal stress. It means that the normal force acting on that particular face is divided by the area of that element to determine the compressive or the tensile stresses in any case. On the other hand, if we want to determine the shear stress, we need to divide the horizontal force, or in some cases it can be a vertical force, but in this case it is particularly the horizontal force, by the area of that element, and it comes out as the average shear stress. A summary of previous discussion is that there are three main steps in determining shear stresses in any body. It can be shear stresses, it can be normal stresses, but since the focus of this lecture is shear stresses, so I've mentioned this thing. The first step is you have to draw free body diagram of that body. Then take a summation of the forces and moments to determine the internal forces at that particular location where you need to determine the stresses. The final step is the stresses are determined as the ratio of the force to the respective area. By respective area, I mean that if you need to determine normal stresses, then the ratio of normal force and the area whose area vector is parallel to the normal force is taken as the respective area for determining normal stress. However, in order to determine shear stresses, you have to take a ratio of the shear force and the area whose area vector is perpendicular to the shear force. This thing should be kept in mind that these area vectors have to be given due consideration while determining normal stresses and the shear stresses. I'll repeat, in case of normal stresses, area vector is parallel to the normal force or the applied force. In case of shear stresses, area vector is perpendicular to the shear force. This marks the end of our today's lecture. If you have any questions, you can post it in the comments. Otherwise, thank you very much for listening me.